So, welcome back student to the next class of nonlinear optics. So, today we have lecture number 57, and in the last class we started Raman amplification process. We will continue with this thing. So, let us quickly go back to our original problem, that we want to find out how the Stokes wave will going to evolve, and in order to find out how the Stokes wave will going to evolve, we need to solve the differential equation that we derived in the last class. So, this differential equation is coupled, and this coupled differential equation tell us that how the intensity of the signal and intensity of the pump will going to change, and if the pump is constant, then in these two equation I can consider I p is constant. So, life will be simpler and I can solve, it seems that I can solve this coupled equation by decoupling some of the equations. So, I will do that today's class, to will try to solve that and try to understand the physics behind these things. But before going to the solution, we like to remind once again that what these two coupled equation basically suggest, which is very important. Then it suggests that one particular component I p divided by omega s plus I s divided by omega s is constant. So, if I now carefully understand what is going on, then this equation I p is a function of z, it is omega p, plus I s is a function of z, which is omega s. This is constant, means I can put the boundary condition here and I can write it I p 0 omega s plus I s 0 omega p, sorry, and it is omega s. So, this equation I can write, because this is a constant. So, even if I change the z, these things will not going to change. So, initially if I have I p value and I s value and calculate I p divided by omega p plus I s divided by omega s, whatever the value I will have at any z point, even though, please note that even though I p and I s both are changing. It is not that I p and I s are constant, they are changing, but the important thing is that even though they are changing, if I add this quantity, then they are conserved. And what is the meaning, what is the physical meaning of that? I p divided by omega s and I s divided by omega s is a total number of, it a measurement of some sort of measurement of the total number of photon. So, this total number of photon before the operation and total number of photon after the operation, before the operation means at the input and at the output, should remain same. So, the total number of photon remain conserved. Another thing, important thing we find from this equation, this equation suggests that the rate, the change of pump photon is equivalent to the gain of signal photon. So, the number of pump photon that will destroy will going to create the same number of signal photon. So, this relation is basically a Mann-Ray-Rowe relation, and it basically tells you the conservation of the energy thing, that is all. So, we have already discussed these things in the previous class, it is just a recap. So, now we are in a position to solve the coupled differential equation. So, if I solve the coupled differential equation, we will have this equation in our hand, and this coupled equation it is now not remain coupled, because I p is constant. If I p is a constant, So, the second equation related to I p, the second differential equation related to I p is 0, or that means this equation, this coupled equation is not remained coupled anymore. So, if I p is constant, then the solution is very quick, one can solve this very easily, that this is my equation where G r I p is a constant. I can put I s here and integrate it over 0 to z, right hand side also I integrate over 0 to z, and the solution is something like that, where we find that I s will going to increase exponentially, which is expected, because we are talking about gain. So, if we solve this differential equation, we must have something in our hand which is having an increment, and in this case this increment is exponential in nature. So, this is some sort of exponential growth. So, once we have the solution, we can readily understand that we have exponential growth in our hand when I p is a constant. That means, physically this is our system. I launch pump omega p and small signal omega s. In the output I have omega p and also omega s, but this omega s is amplified, and this amplification is now exponential in nature. So, this exponential thing depends on z. So, if I increase the length of this material where this Raman process is happening, this material where chi r is there, chi r is a Raman susceptibility term which is inside this G r, mind it. So, then what happened, that we will have enormous amount of signal, but you can readily understand that this is a non-physical kind of solution, because this extra energy, from where we will get the extra energy is, that is from omega p. So, omega, the field related to omega p or the pump. So, pump has to decay. So, in realistic consideration, so pump will not remain constant. So, it will going to decay. So, this structure will not remain same. So, there will be some difference. So, only for initial case when z is very small or the efficiency is small, then only maybe this exponential expression is acceptable. But if we have long distance or the efficiency is large, that means we are generating omega s very efficiently, then this exponential modeling is completely a failure, because physically it will not going to give you anything. But the important thing to understand this exponential model is that, so with this expression you can readily understand that the signal will going to increase without doing anything, without calculation, without much calculation rather. If we have the equation and if we put the condition that I p is equal to constant, then you can readily say that there will be some exponential growth of the signal, or in this case the Stokes wave. Well, now also it is my duty to show you the real case, and this real case happens when we have the depleted pump situation. The depleted pump situation means the pump is now not remain conserved, and d I p dz, d I p dz is not equal to 0. If this quantity is not equal to 0, then that means I need to solve both the equations simultaneously, and I need to decouple this equation and then try to solve. Again, this is not a very tough task to decouple these two equations, because we have an additional equation in our hand and we will go into this additional equation to solve this. What was the additional equation? The additional equation is this relation, which tells us that I p divided by omega s plus I s divided by omega s, I p divided by omega p plus I s divided by omega s, this quantity is conserved throughout the process. That means, if I write very clearly, it should be I p function of z divided by omega p plus I s function of z divided by omega s is equal to constant, that means I 0. When these things is constant, what additional advantage we will have? We can replace I p and I s in terms of I 0, which is a constant. So, this decoupling thing become quite easy, because in order to decouple, what we need to do? We need to just replace this I p in terms of I s, which we can do very easily with this equation. So, from here I p z is equal to I 0 minus I s omega s multiplied by omega p. So, now if I replace this I p here, which we have done in this line, you can see that the equation is solely depend on I s. The left hand side we have I s, in the right hand side we have I s. So, now we need to solve this simple differential equation. So, I just decouple this by using this equation, which suggests that the total photon will remain conserved. So, from that we can decouple one equation which is related to signal, and then we can now in a position to solve the equation. So, if I solve this equation, this differential equation has d s divided by I s multiplied by I 0 minus I s divided by omega s. So, this is a 12th class problem, how to solve this differential equation, and I believe you can do quite easily these things. I can just divide these two things in this way as shown in the right hand side in this way, and in one part we have 1 by I s and another part 1 by I s, but slightly different way. So, if I do this separation, then it will be easier for us to integrate, and this integration can simply give me log of ln of I s with the boundary condition 0 to z with a plus sign, and this basically give us minus of ln I s minus omega s I 0 with the limit 0 to z. These are the two integration we have. So, we can evaluate this integration quite easily. In the right hand side it will be I 0 z r omega p multiplied by z. So, we can very quickly integrate these two things, and if I do this integration quickly, then we have and combine these two together, then we have the expression something like this. Integrate this, combine these two, you will readily get this expression. And now the next thing is to write this equation in the form I s function of z is equal to some function of z. So, I need to find the value of the evolution of I z. So, I can put I z one side and the rest of the part in the other side, which is again not a very big deal. If you do the calculations, the algebraic calculation right in the proper way, so I can put it as a small homework. So, just extract I s from this equation, and if you extract the I s z from this equation, you will landed to this expression. This is the expression of I s under the condition that the pump is not remain conserved, rather it is decaying. Now, after solving this kind of differential equation, the very first thing that we always check is the boundary condition, whether this boundary condition is whatever the expression we have, the boundary condition is really valid for this expression or not. So, in order to do that, what we do that we put this equation, try to find out the value of this expression at z equal to 0. So, obviously, we know that at z equal to 0, the left hand side will be I z equal to 0, I s z equal to 0 or I s 0, which is already in the equation. So, this term will simply be I s 0. So, if you do these things carefully, you will find that if you put z equal to 0, this term will remain 1, will be 1, this term is 1 minus 1. So, this term will cancel out. We have omega s in the denominator and omega s I in the numerator, these two will cancel out and you will simply have I s 0. So, the boundary condition is basically give us the correct result. So, that means it seems that whatever the expression I find is correct, but you need to check that by yourself. I strongly suggest you to please check that by yourself. In the similar way, if I put calculate IP, I will get the similar kind of results and it is easy. If you calculate IP, then you can also calculate IS. There are two ways to calculate IP. You can use the fundamental differential equation, that solving IP dz is equal to minus of omega p omega s gr is IP, and another equation dis dz gr is IP. So, you can solve again in the similar way these two coupled equation, or you have IS in your hand. So, you just make a derivative of these things and you can have IP. So, IP will be derivative of IS divided by GR IS. This is another way, but these things will be a bit complicated. So, it is better to use another process, and that process is IP z. You have another equation in our hand, mind it, omega p plus is z omega s is equal to I 0. Is is known. So, IP will be I 0 minus of these things multiplied by omega p. So, this is another way to find out this equation of IP. Well, I believe you people can do that quite efficiently. So, now the next thing to plot these two things. If we plot these things, you can find that the plot is completely different from the exponential growth, and it is more logical or more realistic plot, and you can see that IS is gradually, this is basically IS. So, IS gradually increasing and goes to some saturated value, which should be, because it is not that if you increase the Z length every time it will increase. So, there will be some kind of saturation. So, with the increment of this length, only thing that will increase in the initial part and then it go to saturate, and IP will go down because it is basically give the corresponding energy to amplify. So, finally, we will say something about the application of this Raman amplification, and this Raman amplification basically applied in Raman laser. It is some sort of lasing action. You can see that you launch omega s and you are getting the amplified omega s. So, one can use these as a amplifier, and in fibers extensively this Raman amplifier is using. The fiber which is made of the silica, if I plot the Raman gain. So, the Raman gain means the it is I mentioned already that GR, which is the Raman gain coefficient GR, which this is a function of delta omega, because it is a function of Raman susceptibility. Raman susceptibility is a function of delta omega. So, it has to be function of delta omega. So, if I plot this GR as a function of delta omega, we will have this kind of curve where the gain is maxima around this, and in the here I plot the wavelength. So, this wavelength suggests that in if I pump here at this point at say 1450, the highest efficiency will be here. So, I will going to generate some kind of Stokes light very efficiently at this point, which is 100 nanometer apart. So, it is this frequency is smaller. So, the wavelength is higher. So, based on this curve we can generate the Stokes wave. This is a very well known curve, gain curve for silica kind of fiber. So, there are material where also we have Raman amplification, and in other cases this gain curve may change. It depends on entirely the material you are using. So, with this note, let me conclude the class here. So, today we learned the complete process of Raman amplification, and in the next class we will start a brand new topic, which is the pulse propagation in nonlinear systems, which will be the last topic. And thank you for your attention and see you in the next class.